Part 1 Okinawa, April 1945. A Japanese resupply barge sits in the shallows off the Higuchi beaches, engines cut crew waiting for the cover of dusk to make their run. The water around them is flat and grey. There is no sound except the tide. What happens next takes less than 90 seconds, and it involves an aircraft the United States Navy had already decided was too dangerous to fly. A lone F4U Corsair drops out of a shallow dive, wings rocking as it lines up the bow. There is no bomb bay opening, no torpedo running straight and slows beneath the surface, no long glide bombing approach that takes half a minute to stabilize. Just 8 thin steel rails bolted under the wings. 8 rockets leave those rails in pairs, walking up the hull with the precision of a man who has done this before, and the barge is a smoking wreck before the pilot has finished his pullout. On paper, that should not have worked. Everything about the Corsair said it was the wrong aircraft for that job. It was designed in 1938 as an interceptor, built to climb hard and fight other fighters at altitude. Its wings were not engineered for heavy, underslung ordnance. The Navy's own carrier qualification boards had spent most of 1943 cataloging everything it did wrong, and they had a long list. The landings were the worst of it. The big Pratt & Whitney engine up front blocked the pilot's view of the deck during approach. The main gear had a tendency to bounce on contact in a way that could cartwheel the whole aircraft off the side of the ship. There were oil valve failures under high-G maneuvering, landing accident rates that climbed in ways that made squadron commanders tighten their jaws when they read the weekly reports. The Navy gave it a nickname, Ensign Eliminator, not because of anything it did to the enemy, because of what it was doing to the young men assigned to fly it. American pilots, on American carriers, on training flights, before they ever saw a Japanese aircraft. That was the reputation the Corsair carried into 1943, a machine that was dangerous to the side that built it. The Navy's solution was practical and not entirely flattering to the aircraft. Marines didn't operate from carriers. They operated from airstrips on captured islands, and on a dirt runway, the Corsair's landing quirks were a nuisance rather than a death sentence. So the plane that had been rejected by naval aviation went to the men who would take anything that flew and make it work. That decision, made partly out of frustration and partly out of necessity, would eventually change how wars at sea were fought. But no one in 1943 knew that yet. What the Navy knew in 1943 was how to kill ships, and they had spent years building aircraft designed around that specific problem. The Douglas SPD Dauntless had proven the concept at Midway. A single 1,000-pound bomb delivered from a near-vertical dive could punch through a carrier deck and reach the aviation fuel and ordnance stored below. The dive itself was the accuracy mechanism. Come down steep enough, hold the crosshairs long enough, and the bomb went where you aimed it. The problem was the approach. 15 seconds in a near-vertical dive under full anti-aircraft fire was a long time. Long enough for the gunners below to find your angle and fill it with steel. The Grumman TBF Avenger carried something more powerful. The Mark 13 torpedo weighed over 2,000 pounds, ran beneath the surface, and could break the keel of a capital ship with a single hit. But the delivery requirements were unforgiving. Low altitude, slow airspeed, straight and a level for the final run, long enough for the torpedo to enter the water at the correct angle and arm before it reached the target. Avenger crews who flew torpedo runs in the early Pacific War did not talk about it casually. You flew straight and slow toward a ship that was shooting at you for a stretch of seconds that pilots described as feeling much longer than they actually were. Both aircraft worked. Both aircraft also announced themselves from miles out. A dive bomber starting its pushover at 12,000 feet was visible to every lookout on every ship in the target area. A torpedo plane starting its low, slow approach was equally conspicuous. Japanese anti-aircraft gunnery doctrine was built around exactly those attack profiles. The tracking solutions, the fuse settings, the crew positions, all of it optimized for targets that came in high and dove or came in low and straight. What neither doctrine accounted for was a fighter, because a fighter wasn't a threat to shipping. Everyone understood that. The Corsair's wing racks in 1943 were rated for a pair of 100-pound bombs, useful for harassing a truck convoy on a dirt road, not for putting serious hurt on a hull made of steel plate. Japanese planners protecting their forward bases and supply routes made a calculation that seemed entirely reasonable. Given the evidence, leave the small craft with light automatic weapons, because dive bombers and torpedo planes are the real danger, and fighters aren't going to sink anything worth worrying about. They were right about everything except what was about to arrive. At the California Institute of Technology in Pasadena, in a department that did not look like a weapons laboratory and was staffed largely by people who had never flown an aircraft in their lives, the answer was already taking shape. Dr. Charles Lauritsen was in his early 50s, Danish-born, a physicist who had come to Caltech between the wars to study nuclear reactions and X-ray equipment. He was the kind of man who could sit with an engineering problem for a long time, strip away everything that was complicated, and find the thing at the center that was actually simple. When the Navy's Bureau of Ordnance brought him into the National Defense Research Committee to work on aircraft rockets, he brought that same quality to the question. The question, stripped to its essentials, was this: what does a pilot actually need in order to put a warhead on a moving ship, survive the pass, and do it again? Not in a test range, in combat, with people shooting back. The answer Lauritsen and his team arrived at was not a more powerful warhead. It was not a more sophisticated guidance system. It was a piece of steel hardware so simple that the engineers who first saw it wondered if they were missing a launch rail. A short metal stub, bolt it to the existing hardpoint under the wing, slide the rocket onto it, done. No bomb bay geometry to redesign, no new structural reinforcement, no specialized ground equipment. A crew with basic tools could mount 8 of these rails on a Corsair in about 30 minutes. 8 rails meant 8 rockets, each one a 5-inch finned weapon on a 3.5-inch motor tube, weighing about 140 pounds, fully loaded, with either a high explosive or semi-armor-piercing warhead capable of punching through the light steel of a ship's hull. The weapon was called the high-velocity aircraft rocket. Pilots who first saw them on their wings called them something so holy Moses. Not a term of reverence, a term of disbelief, because standing on the flight line, looking at 8 of these things hanging under a fighter that was designed to chase other fighters, the first reaction was not confidence. It was a question. You want me to go sink ships with those? The answer, as it turned out, was yes. And the reason came down to physics and arithmetic that no one had fully worked out until they ran the numbers. 8 HVRs carried a combined warhead, roughly equivalent, charge for charge, to the full secondary battery broadside of a light cruiser, delivered by an aircraft that cost a fraction of a cruiser's construction price. That could be airborne within minutes of a call for support, that could operate in water so shallow no cruiser could follow. That could make multiple passes against multiple targets in a single sortie and return to refuel and rearm in the time Teb would take a ship to steam back into position. The question was never whether the rocket was big enough. The question was whether anyone had been measuring the right thing. Perp 2, the Japanese planners who fortified Okinawa, were not careless men. They had been fighting the United States Navy for 3 years by the time the spring of 1945 arrived. They had watched the American industrial machine produce ships and aircraft in numbers that should have been impossible. They had absorbed the lessons of Midway, of the Philippine Sea, of Leyte Gulf. They were not operating on assumptions that had never been tested. The assumptions they were operating on had been tested. They had been tested in 1942 and 1943 against dive bombers and torpedo planes, and those tests had produced an anti-aircraft doctrine that was, by the standards of what it was designed to counter, reasonably effective. The 25mm Type 96 automatic cannon was the backbone of Japanese naval anti-aircraft defense on everything from destroyers down to resupply barges. It was a capable weapon within its parameters. Those parameters included tracking aircraft from about 2,000 feet down to roughly 500 feet across the arc of a dive or a torpedo approach, with a fire control solution that assumed the target was coming in on one of 2 predictable vectors, high and steep, low and straight. No one had written a targeting solution for a fighter coming in at 50 feet, doing 400 miles per hour from a direction that changed pass to pass. It was not an oversight born of arrogance. It was a logical conclusion built on evidence that was entirely correct until the middle of 1944. Fighter aircraft could not threaten ships. The wing hardpoints couldn't support heavy ordnance. The largest weapon a fighter could carry at that point in the war was a medium bomb that would barely dent a ship's deck plating. The threat assessment said worry about the dive bombers, worry about the torpedo plane, the fighters are escorts. They are not the danger. This was the assessment when the HVR entered fleet service in early 1944. No one updated the assessment. In Pasadena, in the Caltech laboratories that fed data to the Bureau of Ordnance, Charles Lauritsen's team had been running numbers that suggested a combinations nobody in naval planning had fully considered. Not the rocket alone, not the Corsair alone. The two together as a system doing something neither was designed to do separately. Corsair's Pratt & Whitney R2000 800 radial engine produced 2,000 horsepower in a package that gave the airframe its distinctive handling. Stable in a dive, responsive in a pullout, fast enough to compress the time window any ground-based gun crew had to track and respond. The wing platform that had made it such a precise machine gun fighter, steady in the aim, predictable in the run, turned out to be equally precise when the guns were replaced with rocket rails. A fighter pilot aiming rockets didn't need to solve the same geometry as a bomb aimer. A bomb dropped from altitude follows an arc that takes time to calculate. A rocket fired from a shallow dive travels on something much closer to a flat line. You point the nose, you walk the impacts toward the target, you correct between shots, and you are through the target area and climbing away before the crew on the deck has had time to settle their aim on where you were 3 seconds ago. The arithmetic that changed everything looked like this. A TBF Avenger torpedo crew spent roughly 40 seconds on the final attack run in effective range of the ship's anti-aircraft weapons. 40 seconds in which the aircraft was committed to a straight, predictable course at an airspeed it could not change. A Corsair making a rocket pass spent 8 seconds in the same engagement window less if the approach angle was steep. The Type 96 cannon needed a minimum of 4 to 6 seconds to acquire, track, and fire on a maneuvering target. 8 seconds was not a comfortable margin, but it was a margin that existed where 40 seconds was very nearly a sentence. Marine Corps squadrons first used HVRs operationally in early 1944, initially in the continuing air campaign around Rabaul. But it was the Philippines campaign that autumn, with its dense network of supply routes, coastal shipping, and shallow water anchorages the Japanese were relying on to sustain their forces, that gave the weapon its first sustained proving ground against shipping specifically. The doctrine did not arrive fully formed. It was worked out in real time, the way combat forces always work things out. The squadrons didn't have a training manual that said low, fast, shallow, walk the rockets. They had the weapon, they had the aircraft, and they had the problem in front of them. What worked got repeated, what didn't work got men killed, which tended to accelerate the learning. What worked was speed and angle, not the near vertical dive of the Dauntless, which committed you to a long trackable approach from the moment the nose went down. Not the flat torpedo approach that made you a predictable target at low altitude for a stretch of time that no experienced pilot wanted to spend in the sights of a ship's gunners. Something in between, a shallow, fast dive that kept your speed high, kept your time in the engagement envelope short, and let you put rockets on a target in sequence rather than dropping everything at once and hoping. The results started showing up in after-action reports with enough consistency that the people reading those reports began to take notice. But Okinawa was where the case was fully made. The Okinawa campaign began in April 1945 and lasted until late June. It was the largest amphibious assault in the Pacific theater, and it came with a specific logistics problem that had not been fully anticipated by the pre-invasion planning. Japanese supply barges and picket boats were feeding the defending garrison from hidden anchorages scattered across the islands and coastline. They moved at night, they hid in coves and inlets during daylight. They were small, numerous, and spread across a geography that made it genuinely difficult to hunt them systematically. A destroyer couldn't follow them into shallow water. A dive bomber needed enough altitude to set up its attack that the noise of the approach warned the crew to scatter before the bomb arrived. A torpedo plane had nothing useful to offer against wooden barges in 2 feet of water. A rocket-armed Corsair could fly 50 feet off the wave tops and arrive before the sound of its engine did. Fast Carrier Task Force reports from that spring noted the pattern with the specificity that military observers use when something else is working well enough to document carefully. Rocket-armed Corsairs and Hellcats were credited with breaking up barge traffic and disrupting the supply chain that was keeping the garrison fighting. Squadron after-action summaries from Marine Air Group units operating out of Okinawa and Aishima described individual engagements in which 2 or 3 rockets from a single low pass were enough to set a wooden barge ablaze or hull a picket boat below the waterline, results that previously would have required a dive bomber's full bomb load or a strafing run that exposed the aircraft for far longer than any sensible pilot wanted to stay over a defended position. The pilots who flew those missions described it in ways that stayed with them long after the war ended. They did not describe it as terrifying in the way torpedo runs had been described by the men who flew them in 1942 and 1943. They described it as something. The long exposed runs that older aviators had trained for required a specific kind of cold deliberateness, willingness to hold course and altitude, while every instinct said, break away. The rocket pass required something different. It required the same skill a fighter pilot already had, the ability to put your nose where you needed it and hold it there through a fast, committed pass. Point the nose, walk the rockets onto the hull, be gone. The psychological weight of that difference was not trivial. A pilot who felt like he was extending his gunnery skills rather than suppressing his survival instincts made better decisions under pressure. He corrected his aim instead of flinching. He completed the pass instead of releasing early. He came back the next day instead of carrying something in his chest that made it harder to climb into the cockpit. Navy ordnance evaluators compiling data after the Okinawa campaign found that rocket-armed fighters were sinking, disabling small craft at a rate that dive bombers, measured ton for ton of ordnance expended, could not match. The arithmetic was not complicated. Fighters could generate more attack passes per hour of flight time. More passes meant more chances to put ordnance on target. More target service per sortie meant the overall rate of interdiction was higher than anything the dive bomber force could achieve against the same class of targets. The critics who said a fighter couldn't carry enough to matter were right about the single rocket. They were wrong about the mission. They were measuring the wrong unit, not the warhead, the clock, and by every measure of time, the Corsair with rocket rails was doing something that nothing else in the inventory could do at the same cost in aircraft, pilot, and hours. It was tempo that decided those engagements, not tonnage. What worked was not the biggest explosion. What worked was the side that could put ordnance on the most targets in the least time, with enough accuracy to matter and enough speed to survive the attempt. The barge traffic feeding the Okinawa garrison was not stopped by a single large strike. It was stopped pass by pass, target by target, in the kind of grinding arithmetic that looks unremarkable in after-action reports and devastating in the aggregate. Harp 3. When the guns went quiet in the Pacific, the United States sent teams of analysts into Japan to answer a question that would shape military planning for the next generation. Not how did we win? They knew that. The question was what actually worked. The United States Strategic Bombing Survey interviewed hundreds of Japanese military officers in the months following the surrender, senior planners, ship commanders, anti-aircraft battery chiefs, men who had been on the receiving end of American air power in every form it took across 4 years of war. When analysts asked about the air attacks that were hardest to defend against, a pattern emerged that cut across seniority, service branch, and geographic theater, not the B-29 raids. The strategic bombing campaign had been devastating, but it was a known danger operating in a known way. You could see the formations coming from a long distance. You could sound the alert, disperse the civilians, position the fighters. The attacks were enormous, but they were not surprises. Not the carrier dive bombers. By 1945, Japanese anti-aircraft gunnery doctrine had adapted to the dive bombing attack profile in ways that made it costly. The approach was telegraphed. The attack vector was predictable. Experienced gun crews could put steel into the dive path with enough consistency that dive bombing over defended targets carried a price. What Japanese officers described in various ways and across multiple interviews was the attack that arrived before they were ready for it. Aircraft that came in below radar coverage, below the effective depression angle of the standard air mounts, at speeds that compressed the response window to something that could not reliably be met by a trained gun crew working within the parameters their equipment was designed for. Low fast, from directions that changed pass to pass. The USSBS transcripts do not record a single memorable line on this subject, but a theme repeated across enough separate interviews that analysts flagged it in their summary reports. In various forms, the observation came back to the same point: we did not have doctrine for aircraft coming from below the water. They did not mean literally below the water, they meant below the expected horizon, below the angle where the tracking solutions worked, below the floor of what the defense had been built to handle. This was not a failure of Japanese courage or Japanese engineering. The 25mm Type 96 was a capable weapon. Japanese AA crews were trained and disciplined. What failed was the threat assessment, written when fighter aircraft could not carry ordnance worth worrying about, never updated when they could. The weapon changed. The doctrine that had to counter it did not change fast enough. Charles Lauritsen returned to Caltech after the war and resumed the work he had been doing before the NDRC called on him. Nuclear physics, radiation measurements, the problems that had interested him when there was no war to interrupt the research. He received recognition from the scientific community for his contributions to wartime weapons development, which were substantial across several programs, not only the HVR. He did not receive a ship named after him. He did not receive a base or an airfield or a memorial in a town square. He died in 9,968 in Pasadena. In the years between the end of the Pacific War and his death, he would have seen the weapon he helped develop used again. The Korean War brought Corsairs back into combat. The aircraft that the Navy had called the Ensign Eliminator and handed to the Marine Corps flew from escort carriers along the Korean coastline against river junks and small coastal vessels that were moving supplies for the opposing forces. The same rocket rails, the same shallow attack profiles, the same arithmetic applied to a different geography against a different enemy. Pilots flying those missions described the same thing their predecessors had described off Okinawa. A rocket pass felt like an extension of gunnery, fast, committed through and climbing before the return fire had settled. A wooden junk carrying supplies along a river channel could be put under in the time it took a spotter aircraft to radio its position to a controller. The weapon that Lauritsen's team had bolt-mounted to fighter wings in 1944 was, without modification, doing the same work a decade later on the other side of the world. The lesson the Corsairs' anti-shipping career demonstrated was not a lesson about rockets. It was not a lesson about fighters. It was a lesson about the relationship between a platform and a mission and the quality of thinking that connects them. The F4U had been designed to intercept aircraft at altitude. Its airframe was built around a specific set of performance requirements that had nothing to do with sinking ships. Its engine gave it speed that was useful in a dogfight and turned out to be equally useful in a rocket pass. Its wing geometry made it a stable gun platform in a turning fight and made it an equally stable rocket platform in a straight attack run. These were not design features that anyone had specified for the anti-shipping role. They were characteristics that happened to transfer. The zero-length launch rail was not an engineering marvel. It was, in its physical simplicity, almost deliberately unimpressive. What it represented was something harder to design than hardware, a willingness to solve the problem that actually existed, rather than the problem the system had been built for. This is the part of the story that military planners and engineers have returned to repeatedly in the decades since, because it reveals something that runs against the instinct of purpose-built design. The Navy did not need a dedicated anti-shipping aircraft to solve the problem Okinawa presented. They needed a fast, sturdy platform and a simple modular weapon that could be mated to that platform without extensive modification. Combination did something that neither element could do alone, and it did it at a cost in time, money, and specialized infrastructure that a purpose-built system could not have matched. What mattered was not what the aircraft had been built to do. It was what it turned out to be capable of when someone's asked the right question and built the simplest possible tool to answer it. The battlefield and the waters around it were not a clean engineering problem where the biggest warhead always won. They were a logistics problem. And logistics problems get solved by whichever side can put ordnance on the most targets in the least time. The Corsair should not have been a ship killer. The Navy said so, the engineering specs said so, the wing hardpoint rating said so, the Japanese threat assessment said so. 90 seconds over the Higuchi beaches said something different. The F4U Corsair was the Ensign Eliminator in 1943. It was, by 1945, one of the most responsive and lethal ship-killing aircraft in the Pacific theater. The same airframe, the same engine, 8 thin rails under the wings and 90 seconds over the water. The trick was not the rocket. The trick was the question.